Welcome back to the final lecture in our exploration of the cosmos. In the previous lecture, I left you with the speculative idea that there may be more than one dimension outside the ones that we see. Indeed, there may be many dimensions, and that most of them are tiny little things, but some of them might be big, and our visible space might be embedded in those big dimensions. All sorts of interesting ideas at the cutting edge of physics. Well, I'm going to continue along the same vein in this perhaps even more speculative lecture. But before we do that, let's get back to ground zero and discuss something that's pretty well established, that's not so speculative. And that is that the Big Bang really did happen. Let's consider the successes of the Big Bang. Almost by design, it's consistent with the expansion of the universe. All the galaxies are receding away from each other. And if we extrapolate this expansion back in time, we come to a beginning of the universe, t equals 0, when it all was in the same place. And that time was something like 13 or 14 billion years ago, 13.7 if you extrapolate things backwards in time. And that's consistent with the measured ages of the oldest stars in the globular clusters. The oldest globular clusters appear to be about 13 billion years old. And if you allow 500 million to 1 billion years for their formation, you come up with, once again, with an age of something like 13.7 billion years. And finally, the studies of the microwave background radiation from the Wilkinson Microwave Anisotropy Probe give the most precise age for the universe, 13.7 plus or minus 0.2 billion years. So the universe is not infinitely old. It had a beginning, and that's a prediction of the Big Bang theory. Yet another prediction is that galaxies should evolve with time. And indeed, here are galaxies billions of light years away that do look different from galaxies today. They looked more scrawny, more messed up, more like train wrecks back then. And they evolved with time to form more stately structures in which, in general, there's less active star formation going on. So galaxy evolution is something that's consistent with the Big Bang theory. So is the fact that hydrogen and helium, the two lightest elements, are spread uniformly throughout the universe and are present in great quantities. They were produced during the Big Bang. The heavier elements seen in this chart are not as abundant as hydrogen and helium, and they're found in pockets. Some regions of space have a greater abundance of heavy elements, others have a smaller abundance, in accord with the idea that stars blow up and contaminate, pollute certain regions of space with the elements that they cooked up deep in their cores and ejected into the cosmos. All these things are consistent with the evolution of the universe according to the ideas behind the Big Bang theory. Well, the Big Bang theory in its standard form, in its original form, though it has many successes, also has certain deficiencies, certain problems, observations that it has difficulty explaining. And in fact, the standard original Big Bang theory has been modified in recent years in its first tiny instance of a second. The Big Bang hasn't been dethroned or anything like that. It's just been modified in the first few tiniest fractions of a second after creation. The problems that we see are that when you look at the microwave background, the temperature of the universe, it's the same in one direction as it is in a completely opposite direction. Indeed, it's the same throughout the sky, except for these tiny little variations which we expected to exist, and from which clusters of galaxies, superclusters, things like that, naturally grew as a result of gravitational accumulation of matter. But other than those tiny fluctuations, it's the same. And that's weird, because the universe was always too big, according to the standard Big Bang theory, for different regions widely separated in space to have ever communicated with each other, using any signal that travels at or more slowly than the speed of light. In the standard Big Bang, it's always too big. Signals can't travel from here to there to tell different parts of the universe that they should be at the same temperature. The standard Big Bang has no real reason for the uniformity of the temperature of the universe, the isotropy of the temperature. The other problem with the standard Big Bang is that it has no clear explanation for the observed flatness of the universe. We observe omega, the total energy density of the universe, to be 1. Yet it would today deviate strongly from 1, either to very large values or to very small values, unless it were exactly 1 in the beginning. If it were forced to be exactly 1 in the beginning, then it would stay equal to unity. But even the slightest deviation from unity in the beginning, either above unity or below, leads to a huge deviation by the time the universe is about 14 billion years old, either 100,000 or 10 to the minus 5 or some other number greatly deviating from unity. And the standard Big Bang has no natural explanation for why the energy density of the universe should be exactly this critical value, such that the average energy density divided by the critical value is exactly equal to unity. It's an arbitrary thing, and in the Big Bang it could have been anything. So those are the two major problems with the standard theory, and there are others as well that are related in one way or another. So in the last 20, 25 years, a number of physicists, including Alan Guth at MIT and Andrei Linde at Stanford, although when he did the work he was in the former Soviet Union, these physicists and others have altered the standard Big Bang in the first tiny blink of an eye of the universe's existence. The theory is seductively powerful. It has many interesting consequences, some of which have already been shown to be correct. The theory is known as inflation. It postulates that the universe started out much smaller than suggested by an extrapolation of the standard Big Bang backwards in time. It started out so small that light or other signals could have brought different parts of the universe into equilibrium with each other to the same temperature. It was all at the same temperature because it was very small, like heat flowing along a pipe, bringing it to the same temperature everywhere. And then the universe went through a whoosh, a gigantic, incredible expansion, an exponential expansion that took it from tiny, microscopically tiny size scales to an essentially arbitrarily large universe. It stayed in equilibrium. Once something is all at the same temperature, it continues to be that way as it expands. It also became very, very flat. Omega equals unity is tantamount to saying that the universe is flat because of general relativity. It was flat because it expanded so much. If you take a little tiny circle and you inflate it exponentially to make it a gigantic circle, you'll get a universe that's far, far bigger than the distances over which we can see. And any space, regardless of how it's curved, appears flat over a sufficiently small area. Again, take Kansas or something. It looks flat, but it's part of the Earth's surface. It's actually curved, but it's hard to tell that it's curved because it's so small. The curvature is so small compared with the radius of curvature of the entire Earth. So that's the idea. Inflation made a humongous universe that locally looks flat. In a graph of the radius of the currently observed universe along the vertical axis versus time along the horizontal axis, the universe started out very, very small, and when it was something like 10 to the minus 37 seconds old, it inflated exponentially to a huge size. Then inflation stopped, and the regular Big Bang expansion continued. Instead of starting out pretty big, as in the standard Big Bang, and getting bigger, it started out very small, became enormous very quickly, and then continued in its standard Big Bang expansion. So in a sense, inflation is what launched the apple. It's what gave it the oomph to get it going through its trajectory. Now this sounds like it's expansion of space faster than the speed of light. We went from something very, very small to something very, very large. And indeed it is. It is superluminal expansion. But that's okay. it doesn't violate special relativity, which says that nothing can travel faster than light. Because special relativity actually says that no signal can travel through the universe faster than light. No information can travel through the universe faster than light. But an expansion of space itself is not information traveling through space. It's an expansion of every centimeter into 2, and then 4, and then 8, and so on. It is not a means by which you can send signals from here to there faster than the speed of light. So the universe really did expand faster than the speed of light, but that is not a violation of relativity. Well, this is all very interesting, but it's kind of a theory that begs some additional evidence. We want as much evidence for this theory as possible. And it's good to consider other possible theories as well. After all, physicists near the end of the 19th century thought that they had figured it all out, that anything remaining in physics was just details, engineering, little things, you know. Not to say that engineering isn't hard, it is, but the point is they thought that all the fundamental physics had already been discovered. Little did they know that the quantum revolution was coming, that special relativity was coming, that general relativity was coming. We didn't know it all at the end of the 19th century, and we possibly don't know it all now. Indeed, we don't have a complete quantum theory of gravity. So even though inflation looks good, and we think it comes about as a result of the breaking apart of the superunified force to maybe the grand unified force and then the gravitational force, and then that grand unified force breaks apart, and the details of how they break apart may lead to some sort of a latent heat that expands the universe or something. You know, though we have some general idea of how all this occurred in inflation, we don't really know the details yet. We don't know what the fields look like. I showed you a few lectures ago an energy versus symmetry breaking parameter curve that looked like this. We don't know that this is the energy that inflated the universe. We don't know whether the curve was shaped like this or some other way. We don't really know the details of inflation. And in fact, even the broad generalities of inflation might be wrong. There could be an equally viable, equally successful hypothesis that explains the observations. So let's consider some possibilities that have been proposed in the past few years. One was proposed by Paul Steinhardt of Princeton University, one of the originators of the inflation theory. He proposed that maybe, in fact, inflation didn't occur, but instead that our universe has been essentially an infinite parallel plane spread throughout space like a membrane in a higher dimensional universe. And perhaps there are other membranes of this sort that are parallel or achieve a condition of being parallel. And they're cold and lifeless. And then when these planes collide, they heat up. And they produce matter and energy, which later becomes galaxies and stuff. So there wasn't really a Big Bang in his model. There was always a gigantic, cold, planar universe, like a membrane floating through some hyperspace. And it collided with some other membrane. And this could happen many times. There could be many such planes colliding with each other. So in fact, even though now our universe is expanding and becoming colder and more dilute, someday it could in fact collide with another plane. Indeed, he thinks that the acceleration observed in the universe is the movement of our plane toward another one. So we're headed for another collision, maybe. This is a cyclic theory of the universe. I, right now, don't find it particularly compelling because it presupposes the existence of these parallel planes sitting around in space. So it seems to me that something like inflation was required to produce those planes to begin with. It seems like he's starting out with initial conditions that are kind of unlikely. Another idea is that the speed of light has been variable over the past history of the universe, especially when it was very young. Remember I said that the problem with the uniformity of the temperature is that no signal, not even light, could have traveled fast enough to tell different regions of the Big Bang universe that they should be at the same temperature. Well, a theory suggested by João Magalhães is that there was actually a faster speed for light when the universe was really young. And this may have allowed the universe to have come into equilibrium with itself by having these signals traveling faster than the speed of light. Unfortunately, there's not much real evidence for variations in the speed of light, especially variations as big as those that he would like. But this theory has been much publicized in the last year by a book that he wrote that's quite interesting. One possible reason for thinking that the speed of light is changing is that there's a constant of physics known as the fine structure constant. It's the square of the charge of the electron divided by Planck's constant divided by 2 pi. That's what h bar means. Divided by the speed of light. There's some evidence that alpha might be changing with time. Now, alpha, the fine structure constant, is a measure of the strength of electromagnetic interactions. How strongly do electrons feel other electrons in an atom? And how strongly do they feel the proton? And the fine structure constant dictates the energy levels in atoms. Now, if the fine structure constant changes with time, then at least one of the quantities, charge of the electron, Planck's constant, or speed of light, must be changing, maybe even all three. And the evidence that has been suggested is that measurements of absorption lines in the spectra of very distant quasars show possibly a different spacing than they do in a laboratory gas. So here's the spacing between two lines produced by a single element in the laboratory. And here are these same two lines produced by the same element, but at a high redshift, redshift 1. And it looks like they're different. If they really are different, then the fine structure constant must be changing, because those energy levels are dictated by the value of the fine structure constant. However, the measurement that those wavelengths or their spacings have changed is still not completely secure. It's not completely compelling. Moreover, even if the spacings of the energy levels have changed, they've changed by only 1 part per 100,000 by redshift 1. That's too small to be consistent with the variable speed of light hypothesis that I just discussed. And yet it's too large to be consistent with elementary particle theories that have had some success in unifying the different forces, like the electroweak force. So this measurement is neither here nor there. It's too small to be of utility, but too large to be consistent with existing theory. So a lot of physicists and astronomers suspect that the measurement is somehow flawed. Keep an eye out on this in the next few years. There will certainly be more studies of this and more progress made. But we really don't know whether any of these constants are changing with time. Another idea is called MOND, modified Newtonian dynamics. Take a look at this spiral galaxy here. You will recall that I said that the outer parts orbit just as fast as the inner parts, and that, according to general relativity and regular Newtonian gravity, suggests that there must be a lot of mass out here, causing parts that are distant from the center to rotate fairly rapidly, as opposed to, say, Pluto, which revolves around the sun pretty slowly because it's far from the sun and there's not a lot of dark matter in our solar system. Basically none, we think. Well, dark matter is the conventional explanation for this, but you could postulate that gravity behaves in a different way when you're measuring things far from a central point mass. If the accelerations are small, 10 to the minus 8 centimeters per square second or less, and by the way, on Earth, the local acceleration due to gravity is about 1,000 centimeters per square second. So if you're 11 orders of magnitude down from that or less, Mordecai Milgrom in Israel has suggested that gravity behaves in a different way, modified Newtonian dynamics. And he can explain the rotation curves of spiral galaxies. It's a very clever idea. Unfortunately, it appears as though clusters of galaxies are not well explained by this hypothesis. If you look at the hot X-ray emitting gas in clusters, you find that the temperature distribution is nearly equal everywhere. Over a big portion of the cluster, it's the same temperature everywhere. The gas is moving with the same speed. It's jiggling around the same amount. And that, in conventional theory, suggests that mass is spread throughout the cluster. And indeed, we see stars and gas and stuff throughout the cluster. Whereas in modified Newtonian dynamics, you get an inconsistency. But the people working on this are fairly clever, and it's possible that they'll come up with a solution. Maybe the model is deficient as it now stands. But there are problems with it in explaining the observations. So right now, it's not nearly as good as general relativity and dark matter and inflation and all these kinds of things. So those are some of the ideas that are floating around. Since inflation seems to be the one that works best, and since no violations of general relativity have been found, not in astrophysical situations, nor on Earth, I'm going to now go back and assume that general relativity is the correct theory for the large-scale structure of the universe. And I'm going to also assume that inflation, or something like it, is the correct theory for the early, tiny beginnings of the universe's existence. So if you take inflation seriously, the universe is truly gargantuan. I mean, it is huge. You know, you thought there were a lot of galaxies in the Hubble Deep Field. Remember I said that this is a fraction of the sky that's a grain of sand held at arm's length, yet it contains 1,000 galaxies. And that if you extrapolate over the whole sky, you calculate that there are 50 to 100 billion galaxies out there. Well, that's in the observed part of the universe. Inflation theory suggests that the true universe is so much bigger than the observed part that it's not even funny, okay? Well, I just laughed, so it is funny. But that's because I'm easily amused, all right? According to inflation theories, it is quite possible that the ratio of the radius of the total universe to the radius of what we can see, the observable universe, which contains these 50 to 100 billion galaxies, is in fact larger than the ratio of the radius of the observable universe to the radius of a proton. I mean, a proton is about yay big, and I exaggerate by many, many orders of magnitude. The size of the observable universe to the size of a proton may be smaller than the ratio of the size of the whole universe to the size of the observable universe. I mean, that's a big universe. And in fact, inflation suggests that it might be even bigger. The universe could be a Google times bigger than our observed volume, or even a Googleplex, 10 to the 100 times bigger, maybe. In fact, in inflation, it can be arbitrarily large. It is truly an immense universe. And this brings up the interesting speculation by Max Tegmark at the University of Pennsylvania and others, that if the universe is sufficiently large, and if there's only a finite, accountably finite number of possibilities in which ways, you know, particles can arrange themselves and stuff, then it's possible that within the entire universe, there are exact copies of you sitting here listening to the exact words that I am saying, because I am saying them out there in some other part of the universe which exactly duplicates our universe. In other words, if there's only a finite number of possibilities for the configuration of particles and their interactions, and an infinite universe, then in fact, eventually things repeat. Now, don't get too worried that you'll ever meet your clone out on the street. This duplicate universe that mimics ours is so far away that it's just inconceivable. The numbers are larger than astronomical. Nevertheless, the idea is that somewhere out there are duplicates, and elsewhere near duplicates, where maybe I just scratched my head, or didn't, or you scratched your arm, or took a drink of water, or something like that. So all these universes possibly repeat. Now, I'm not sure I buy this. It could be that the number of possibilities, when you take into account quantum mechanics and everything, is uncountably infinite. And in that case, even in a countably infinite universe, you will not go through all possibilities more than once. But anyway, this is a speculative, interesting idea, and it's discussed more in the May 2003 issue of Scientific American by Tegmark. Well, let's consider another possibility, and that is that inflation, as shown here, produces many different inflating volumes that are in fact physically distinct universes. You see here a whole bunch of little hills growing out of what was initially a uniform sheet in some hyperspace. Here's a whole bunch of inflating volumes, all kind of independently inflating. And in fact, in those distinct inflating volumes that are separate from one another, this is now much more separate than parts of the universe that we simply can't see. These are actually separate inflating volumes, physically distinct inflating volumes. It could be that the constants of nature differ from the values that they have in our own universe. Now, in string theory, the hope is that theorists will find only one possible way in which the universe could have been built, only one value for the fine structure constant, only one value for the ratio of the proton to the neutron mass. They hope that they will find the theory that tells us exactly how the universe is, if not why, then exactly how it is, and that this is the only possibility. But many other physicists, including myself, think that the laws of nature may be fixed in some way, but that the constants of nature, the physical constants, might be arbitrary and might be accidents of the way in which the universe evolved in detail early in its history. Accidents in the way in which symmetry broke between the different unified forces. And to give you an example, here's a magnet heated to a high temperature, and all the little magnetic axes point in random directions. Now, when you cool that magnet, what you find experimentally is that domains form where the magnetic fields all point in about the same direction in one region, in a different direction in another region, and so on. And if you heat this magnet up again, it'll become all jumbled, and if you cool it down, the magnetic domains will form in different places with different positions and different directions in which they're pointing. It's a random process that depends on relatively uninteresting details of exactly what atoms of iron were moving around near some other atom at the time they cooled down. You know, it's just accidents of nature. And in a similar way, the way in which symmetry broke, the way in which the fields became ununified as the universe cooled, could have been relatively uninteresting accidents of nature. And the value of the fine structure constant, like the axis of orientation of these magnetic domains, may be essentially a random variable, taking on different quantities, different numbers, different values in these different universes. Okay, that's one idea. It's even possible, according to some theorists, that the laws themselves are different in these different universes. And this I illustrate with bulbous universes having different colors. The laws themselves, the physical laws, might differ if in these different inflating domains, different numbers of dimensions became small, say 5 instead of 7 or 6 or 2. And depending on the size to which they compactified. These are all things for which string theory has no current explanation, and it's conceivable that there are different ways in which all this could have happened. Moreover, universes might even spring from nothing, having different properties. Jay Pasachoff and I described this theory, which was originated from other people, but we describe it in an article we wrote for the Astronomical Society of the Pacific, and the idea is that universes might spring forth from quantum fluctuations out of virtually nothing. And then they grow to an immense size as a result of inflation. And the physicist who thought of this idea, Edward Tryon, said, in answer to the question of why it happened, I offer the modest proposal that our universe is simply one of those things which happen from time to time. So it might happen many times with different values for the physical constants, and maybe even different laws. And then finally, there's the idea that universes might be born out of the singularities in the middle of black holes. So here's a picture of a black hole, and from the singularity in that black hole bursts another independent universe. That's an idea that's being bandied around among theorists. So there may be many ways to produce universes, and there may be many different physical characteristics to those universes. Now, how will we ever know? How can we test for other universes? Well, they're not directly observable. They're other universes. But if all the other predictions of a theory that leads to other universes are shown to be correct, if there's much experimental verification of the underlying theory that suggests the presence of other universes, then that lends credence to the idea that the theory is correct in predicting other universes as well, if all of its measurable consequences are correct, okay? It doesn't prove that it's right. We'd like to see other universes to prove that it's right. And one way in which that might be not science fiction in the future, but an actual scientific reality, is if we find ways to communicate through rotating black holes or through other bizarre connections between different spaces called tunnels or wormholes. Here's a graphic representation of one of these things. If you have a tunnel from universe A to universe B, you might be able to send light signals or other signals between these universes and thus find out how universe B differs from universe A, if in any way. Now, I discussed in my first course how you might be able to travel through a rotating black hole or some sort of a wormhole if there existed matter that can keep the throat of a wormhole or a black hole open. You need essentially matter with negative gravity, a repulsive sort of matter. Kind of like what we think is accelerating the universe, but here you need it to be local. You need to make a spacesuit out of it, and we know of no such material. It's not theoretically impossible, but we don't know of it, and it doesn't really jibe well with current theories. If such a theory is correct, however, it also means that you could communicate, or even perhaps travel to, other parts of our own universe through shortcuts. See, this is a shortcut. This is a tunnel that allows you to go from A to B without having to go the long way around. So you took the short way home, okay? And maybe, you know, some sort of aliens have figured out a way to keep these tunnels open and to travel from one part of the universe to another. Maybe that's how they got here, according to some tabloids. You know, you see headlines like "Alien backs Clinton" about a decade ago when he was running for the presidency. And some years later, it looks like the same alien endorsed Bush. So either all these aliens look alike, or this alien changed political alliances in the intervening years. You know, maybe it's something the Democrats did or something. Well, of course, if you believe these headlines from the tabloids, you probably believe ones that say Noah's Ark found on Mars. That was one I recall from Weekly World News after the discovery of water ice on Mars. Noah's Ark found on Mars. Bible shocker. Wow, you know. So don't believe everything you read. Well, getting back to all these multiple universes, as graphically shown here, if we're the blue one, let's say, or let's say this green one, all right? We're just one of many, possibly, okay? And the other ones may have different physical constants, if not different physical laws. Well, this could help explain why our universe appears to be so finely tuned for life. I mean, look at our universe. Everything is right for us, for our existence, for complexity to have arisen. Indeed, complexity of the type that leads ultimately to sentient beings that can think about all this and ask questions. If there's only one universe, why should it have been built this way? Now you might say, why not? Isn't that just as good a way as any other? Well, maybe, but this is debatable. There are many ways in which it looks as though the properties of nature are geared toward the development of complexity. For example, if the strong nuclear force were only 20% weaker relative to the electromagnetic force, then there would be only hydrogen in the universe. There wouldn't be the whole periodic table. There would be no chemistry. There would be no biology. There would only be hydrogen. Conversely, if the strong nuclear force were only 2% stronger, then there'd be no hydrogen. There'd only be heavier elements, but there wouldn't be water. There wouldn't be hydrocarbons. There wouldn't be fusion of hydrogen in stars. If the weak nuclear force were a little bit stronger, again, you'd have no hydrogen. If the mass of the neutron were slightly bigger than it is relative to the proton, you'd have only hydrogen. Again, a boring universe. If gravity were stronger, stars' lives would be short, possibly not allowing intelligent life to develop, ever. If the cosmological constant were somewhat bigger than it is early in the universe, matter would have flown apart so quickly that no galaxies and no stars would have formed. And there's a plethora of other examples. It's as though the constants arrange themselves in a manner to produce a universe that can lead to complexity, life, and the pinnacle, intelligent life. It need not have been this way, we think. Now, I'm not saying that ours is the only good universe. There might be other good ones as well, where the particle masses and the forces and stuff are just right for the creation of complexity. But you can easily think of a multitude of boring universes, a far larger number of boring universes, stillborn universes, where this sort of complexity never develops. Okay? So ours might be a rare kind of universe. This is a sort of reasoning known as anthropic reasoning. It basically says we're here, therefore conditions must have been suitable for our existence. There had to have been carbon, for example, because you can't make interesting chemical bonds only out of hydrogen. Now, this is a topic that many physicists feel is really outside the realm of physics. They say, well, you know, this is not testable and all that. And so they dismiss it entirely. But I think it is of some utility. Consider, for example, the early Greek philosopher contemplating the planet Earth and wondering why it has the particular mass, radius, and distance from the sun. In the Aristotelian cosmology, the Earth was unique. It was a constant of the universe. And the Greek philosopher may have wondered what the fundamental physics is that governs the properties of the Earth. What is the fundamental physics that gives it the mass that it has, the radius, the distance from the sun? Just as the string theorist of today is wondering what the fundamental physics is that gives the proton the precise mass that it has, and gives the strong nuclear force the precise value that it has. They're all looking for the way it must be and for the reason. Well, maybe there isn't a reason. The Greek philosopher could have thought, well, maybe these are random accidents, and that the fundamental laws say nothing about how, in detail, the mass of a planet should turn out, or its radius, or its distance from a star. The Greek philosopher could have reasoned that, in fact, as long as our Earth has properties within a certain window of parameters, certain radius, certain distance from the sun, it would be big enough and warm enough and so on to support life. So the philosopher could have reasoned that we're in some window that's good, and that there's many other planets that are not within this window in which life could have developed. Now, it makes sense to talk about an ensemble of objects populating a range of values for the physical properties only if that ensemble really does exist. It doesn't really make sense to talk about an ensemble and then say there's only one example. So the Greek philosopher could have come to the conclusion that other planets may well exist without having directly seen any other planets. Wow. In a similar way, we can say that maybe other universes exist that cover a wide range of properties randomly, even though we haven't ever detected them. Now, there's one other idea that's an extrapolation of this. Lee Smolin has suggested that if universes are born out of black holes, like in this diagram, and if they pass on their properties to their baby universes with only a few small changes, like tiny mutations, and if the universes that are best at producing black holes are also the best at producing life, then eventually there'd be sort of a takeover among the universes that produce black holes and produce life. Because the black hole producing universes produce more progeny, and those progeny produce more progeny. And if those universes are the ones that are best at making life, then Lee Smolin suggests that our universe has physical properties which are not just randomly taken out of the entire random, equally probable distribution, but that there's a great probability of having universes that have life because those are the very universes that produce black holes. It's an interesting idea of natural selection among universes and their progeny. You mutate, mutate, mutate until you find a universe that's really good at producing black holes. And it produces lots of other universes like itself. And his idea is that maybe those universes are also the ones that are best at producing life. Wow. I warned you that this would get pretty speculative, okay? I warned you. But this is what people are thinking about right now. This is what they're considering. Well, these are the frontiers. We don't know where they will take us. I would love to be around in 100 years, 1,000 years, or 10,000 years to see where human exploration of the universe takes us, or of biology, or chemistry, or any field. I would love to be around in the future to see where we go, because humans have almost this limitless potential for inquiry, for solving problems, for figuring things out. And I hope this course has shown you how much we've figured out about the universe and has given you additional insights into the cosmos and this grand universe, be it only a single one or one of many in which we live. And I hope I've also inspired you to keep learning, to learn more about the universe. I thank you for taking the time to listen to me. I know that it is rough going at times. These are things, these are ideas at the cutting edge. But I certainly had a fun time preparing and delivering these lectures, and I hope to do more in the future. You can continually find updates on the web on a lot of the latest observations and theories. Here are some of my favorite websites that you can turn to. Mine, called astroalex.com, provides a lot of links to other sites. Or you can go directly to some of the other sites like those of the Astronomical Society of the Pacific, or pictures of Hubble, Space Telescope discoveries, or a new picture of the day from all fields of astronomy going to this APOD site, or space.com that has lots and lots of neat information. You should go to those websites if you're interested in the daily activities of astronomers and what they're discovering. You might also want to participate in this search for ET, of signals from space, from some other extraterrestrial intelligence. It would be grand if we were ever to find this. You can download a screensaver that computes away while you sleep. It takes radio signals from a radio telescope and analyzes them to see if they might be signals from ET. It's the SETI at Home project. Well, in looking back at what we've covered, again, I continue to be astonished by human progress. We have these incredible brains, this incredible curiosity, this incredible ability to figure things out. And as far as we know, we're the only creatures on Earth ever to have had this ability. And we don't know of any other creatures elsewhere that have this ability. Regardless of whether there are others out there, the fact that we have curiosity and can comprehend the universe through experiments, observations, and deep thought behooves us to not squander these abilities and to use them, to use this gift to our full potential. Richard Feynman perhaps said this best in a poem. He was talking about how life emerged from the lifeless sea. As molecules came together, eventually formed self-replicating molecules, then crawled out to the dry land and evolved into sentient beings that can stand and think and wonder. And he said at the end of his poem, "Here it is, standing, atoms with consciousness, matter with curiosity, stands at the sea, wonders at wondering. A universe of atoms, an atom in the universe." Thank you.